Okay,
Okay, welcome back. This is the second NCGNT seminar of this afternoon. So the second speaker is Zhaoting Wei from East Texas A&M University, and he's going to speak about non-standard holomorphic structures of line bundles on the quantum projective space. Please.
okay, thank you. Thank you for inviting me to talk about this topic. Uh, yeah, I think the first thing is I would like to mention that this work is a project supported by NSF. It's a REU research experience for undergraduates at East Texas A&M University. And I should say that uh, all of my co-authors, Graveman, LaRue, MacArthur, and Passin, they were undergraduate students when we do this research. And I think three of them already they will join graduate school in the autumn, and one of them is still undergraduate student. And I think Passin is in the audience. Okay. Okay, so let me start. Yeah, we'll first have a quick review of quantum CP1, and then talk about gauge equivalence, and then talk about existence of non-standard anti-holomorphic structures. So I think Dr. Guin gave an excellent introduction to the framework to the topic, so I can be quick on the first part. So first, what is a non-commutative complex manifold? So we just use differential calculus to replace the chart and every structure. And in particular, we need to have omega PQ and partial operator, partial bar operator, and integrable conditions, etc. So and so I don't go to too much details, and I should say that we can define quantum CPN. So basically, the idea is CPN is a homogeneous space of group actions, and we can just impose a complex structure on it. So quantum CPN is a homogeneous space of quantum group actions, and they are established work in along this direction. And in my talk, I will mostly focus on CP1Q, but most construction, the standard construction works for CPNQ. So what is CP1Q? So first we talk about the algebra, the coordinate algebra of quantum SU2Q. And it's just generated by A and C and satisfies a bunch of relations. I think, yeah, it's a star algebra. So we have an involution on it. And there's a star subalgebra of this ASUQ2. We call it ACP1Q. So it's just generated by three elements, B minus, B plus, and B0. Yeah, they also satisfies a bunch of relations. And so this is the algebra we're mostly concerned on. So what I would like to say is technically, these relations is quite complicated. The main reason is this relation is not homogeneous. Yeah, so the non-homogeneous makes the thing very complicated. So I would like to comment that in non-commutative geometry, there's another object is non-commutative torus, which is well studied, and that relation in non-commutative torus is homogeneous. It's non-commutative, but the non-commutative relation is homogeneous. So I think, at least in my mind, this makes non-commutative torus much more comfortable to work with than the quantum CP1 because this one is non-homogeneous. Okay, so in the classical case, I think we can say that B0, B plus, B minus, they correspond to these coordinate functions. And we can equip this algebra with a differential star calculus and integrable almost complex structure. So make it a non-commutative complex manifold. So we will talk about it a little bit later. So one thing I would like to say is this ACP1Q is not a C-star algebra yet. But we can have a C-star completion of it to make it into a C-star algebra CCP1Q. And luckily, we have the standard faithful representation of this C-star algebra on the bounded operators of L2. Is just B0 is just like multiplies by a number, and B plus is like shift to the right, and B minus is like shift to the left, and both by multiplying by certain number depending on Q. And so they definitely satisfy the same commuting relations as before, and it's a faithful representation. Okay, so by the way, of course, this representation only works for Q strictly between 0 and 1. So if Q equals to 1, then this is definitely not faithful. Yeah. And a good thing is, first, B0, we already know that it's a self-adjoint operator. And with this standard representation, it's easy to see that B0 has norm 1, and also its spectra is very clear. It's just 1 is and Q squared, Q to the fourth, etc., and 0. So of course we can consider it as Q to the zeros, Q to the twos, Q to the fourths, etc., and Q to the infinities, which is 0. Okay, and 0 is the only cluster point of the spectrum, B0. So that's some properties we want to use soon. Okay, so now what's the complex structure? So we can first talk about the quantum line bundles on CP1. So I think Dr. Guen already introduced it. So we follow the paper of Kakley, Landy, and Sujikam. So we follow their in a notation. They have a very good definition of quantum Ln. And they actually corresponds to the ordinary line bundle O negative n in algebraic geometry on just ordinary CP1. Okay, so one good thing is in the differential star calculus, we have bimodule isomorphism. This omega 0, 1 form is isomorphic to L negative 2. And in this viewpoint, the partial bar operator, we can just have an explicit formula of partial bar operator on the generators. The partial bar B0 is negative Q to the negative 1 over 2 CA, and partial bar B plus is Q to the 1 over 2 C square, and partial bar B minus is negative Q to the negative 1 over 2 A square, and extend by the Leibniz rule. And in our CP1 situation, the flatness is trivial because we don't have omega 0, 2. So the partial bar square is definitely 0. And another good thing is partial bar operator can be extended to a closed operator on the C-star algebra. Yeah. So of course, it cannot be defined for all elements in the C-star algebra, but yeah, at least it's a densely defined closed operator. Okay. Okay, so now some more definitions. So we can define left connections, flat holomorphic, anti-holomorphic connection. So this gives left holomorphic structure on vector bundles. And we can also define the right thing. And since we're working with non-commutative geometry, so we need to be a little bit more careful about bimodule holomorphic structure because we need this switch flap or switch map phi e so that everything works. So the bimodule connection depends on this isomorphism phi. And on Ln, we have the standard anti-holomorphic connection introduced by Kakley, Landy, and Sujikam, in their work. And luckily is this standard anti-holomorphic connection is a bimodule connection. So they constructed this bimodule isomorphism phi n, and everything works. And moreover, they computed the cohomology group and the H0, they have found that the dimension is n plus 1 for n greater equal than 0, and is 0 for n smaller than 0. And actually they found that we have this algebra structure, this ring structure on the H0. So which makes so this isomorphism is interesting because the right-hand side, uh, to me, the right-hand side is the non-commutative ring to define the non-commutative projective space in the non-commutative algebraic geometry. So we can use this ring to define just non-commutative projective space in this way. Okay, and also another result is the H1 group is 0 for L0. So yeah, this is also very useful. Yeah, we'll use it in the future. Okay, so far we have many analogs between the non-commutative and commutative case. And so a natural question is the anti-holomorphic connection on Ln unique or not? In the naive sense, it's definitely not unique because we can add a differential form so that we can get a new connection, new left connection. So again, we need to be a little bit careful because we need this phi n to make it still a left connection and it's also compatible with the function multiplication, etc. So we cannot just simply tensor theta on the left. We need to tensor it on the right and switch it and flip it. Yeah.
Sorry,
Okay.
just a question. Phi is what? The bimodule map.
Excuse me? What?
What is phi again?
Phi? Yeah, the phi is the map that switch.
It's the map for the bimodule connection. Yeah,
Yeah.
perfect. Thank you.
Yeah, sure. Okay. So with this, we can say that two left anti-holomorphic connections are gauge equivalent if and only if there's invertible endomorphism such that they maps one to the other. And Landy and Sujikam, they asked in their paper, they raised the question that is the anti-holomorphic connection on Ln unique up to gauge equivalence? So that's the meaningful question. And as we will see that we will give a negative answer to this question. And before we proceed, we want to first give a more clear understanding of the problem. So the first thing is an endomorphism of Ln itself is the same as the ring of algebra on CP1Q. And since the 0, 1 cohomology is 0, so for any theta which is 0, 1 form theta, we can find a function such that the partial bar of this function equals to this theta. So this is a good thing. So now we can talk about and moreover, we want to consider the C star completion so that we can take infinite sum of functions. So the more precise question of gauge equivalence is if we have a function, can we find an invertible element in the C star algebra, which is also in the domain of partial bar, and the inverse is also in the domain of partial bar, and it satisfies this equation, partial bar G equals to G times partial bar F. And similarly for two functions, if we can find such G such that they give the gauge equivalence. So this is the precise question we are asking. So by the way, there's a technical problem so we expect that if G is in the domain of partial bar and G is invertible, then automatically G inverse will be in the domain of partial bar, and it satisfies partial bar G inverse is negative G inverse partial bar G times G inverse. So that is what we expected. But unfortunately, I cannot prove this. It's not as easy as it seems to be. So we don't have the quotient rule in the non-commutative calculus. We have to use definition approximation to find to see whether G inverse is in the domain of partial bar. But it seems that it's more difficult than we expected. So we have to include this as part of the definition. We want both G and G inverse is in the domain of partial bar satisfies this. Okay.
Wait, why do we want G inverse in the domain? Is that necessary for gauge equivalence?
Let me see. Why do we want G inverse in the domain? Yeah. G inverse. If yeah, I should say that I think so. So yeah. So yeah, it should be the case. Yeah. Yeah. Okay. So anyway, so let's just so by the way, this is a technical problem. So another point is since we have tensor product and the standard anti-holomorphic connection is a bimodule connection. So we can, if we have two gauge equivalent, if we have gauge equivalent class of anti-holomorphic connections on one of the Ln, then we can just use tensor product to move it to Lm. So they are one-one correspondence. Yeah, so this means that we only need to find the gauge equivalent class of anti-holomorphic connections on L0, and then it works for all Ln. Yeah. Okay, so let's just talk about our first attempt to solve this problem. The point is, in the commutative case, the problem is trivial because if we want to find a G, then we just need to use exponential functions. G equals to exponential of f, and then it automatically satisfies this equation. And in the non-commutative case, this exponential function itself does not work. Okay, so now we just look at a simple case. So as we said, the whole C-star algebra is complicated, but the C-star subalgebra generated by B0 is relatively easy. And in particular, it's because B0 is a self-adjoint element and its spectrum is very clear. And also, the partial bar B0 and B0 itself, it satisfies this homogeneous non-commutation relation that partial bar B0 times B0 is Q squared times B0 times partial bar B0. So using this relation, we can see that the partial bar B0 to the nth power, we can just write it as just 1 plus Q squared plus dot dot plus Q to the 2n minus 2 B0 n minus 2 partial bar B0. So this means that although the partial bar doesn't satisfy the Leibniz rule in the ordinary sense, it satisfies this so-called quantum Leibniz rule or twisted Leibniz rule. So we can use the quantum integer to modify the exponential function. So this means that, yeah, for f equals to B0 or f equals to any number times B0, this G equals to k to the nth times B0 to the nth divided by this quantum factorial. Of course, sums from n goes from 0 to infinity. It satisfies this exponential relation. Yeah. Okay, so that's a formal solution. So now the problem is the radius of convergence. So the interesting thing is since Q is smaller than 1, strictly smaller than 1, so this quantum denominator is smaller than the actual n factorial. So this makes the radius of convergence not infinity. Instead, we can see that this thing is actually, the quantum n is actually converges to a number that is 1 over 1 minus q squared. Yeah, so this is the first major sharp difference between the quantum case and the ordinary case. That is, the radius of convergence is 1 over 1 minus q squared instead of infinity. So this means that this power series solution, it only works for k's absolute value smaller than this 1 over 1 minus q squared. It diverges for k's absolute value greater than 1 over 1 minus k squared. Yeah, so this is the first hint that maybe we don't have, we have non-standard holomorphic structure. So of course, this is not the solution because the power series diverges doesn't mean that we cannot find a solution. It just means that this solution doesn't work. So, well, we cannot rule out the possibility that there are solutions in another formula. So we need to find some other method. This method is yeah, we use the condition that the zero cohomology is C. So which means that the only holomorphic functions, just holomorphic functions, in the standard holomorphic structure on the quantum CP1Q is only constant functions. Okay, direct consequence of this is if this exponential equation partial bar G equals to G partial bar F has an invertible solution, then any solution must be a complex multiple of this invertible solution. Yeah, this is a simple but very useful result. Yeah, I don't think it's difficult to prove. It's just because the cohomology is just C. So anything must be a multiple of G, and this multiple must be a constant, must be a holomorphic function. So it must be constant number. Okay, so a directly corollary from this, if this same equation has a non-zero and non-invertible solution, then it cannot have an invertible solution. Yeah, I think the logic is clear because if it has a invertible solution, then any other solution must be a complex multiple of this invertible one. So this other solution must be either also invertible or identically zero. So if we had a non-zero, non-invertible solution, then it cannot have an invertible solution. So this is the main tool we want to use to show the existence of non-standard holomorphic structures. So by the way, I would like to say that we want to use the same results to study the problem that whether two functions are gauge equivalent or two forms are gauge equivalent, but we don't have analog of this result. So this means, yeah, we need to find other ways. So these two equations seems to be similar, but actually one has this corollary and the other has not. That doesn't have it. So yeah, it is a technical problem again. Okay, how to use this result to proceed? We just use the C-star subalgebra generated by B0. And so we have functional calculus to map this C-star algebra to the continuous functions on the spectrum of B0. And recall that the spectrum of B0 is clear. It's just a subset of 0, 1, and moreover, it's just 1 q squared q to the fourth and 0. Okay, so what are continuous functions on this set? The only continuous property we need is the limit of k goes to infinity, q to the 2k equals to f0. Otherwise, it can be very arbitrary. And what are invertible functions on this set? It's just every point is non-zero. So the value is non-zero on every point. So that is enough. Okay, we just work on this subalgebra. And also the partial bar operator satisfies this relation. So inspired by this, we just defined the delta bar operator on these functions, continuous functions on the spectrum of B0 is just on the x to the nth on the generators, monomials is just defined in exactly the same way. So by the way, I think people studied this operator maybe 100 years ago. I think it's called Jackson derivation, Jackson Q derivation or something, I think. Yeah, but we just use this to just in our study again. Okay, so the first thing is this is not a derivation in the naive sense. It doesn't satisfy the ordinary Leibniz rule. It satisfies a Q Leibniz rule, but we don't need that property in our work. And the point is we can just rewrite it in a slightly neat for abstract form. Is delta bar f is fx minus fq square x divided by x minus q square x. So we can see that in monomials, it's just exactly the same thing as before. And in, yeah, and we can just extend, this can be extended to a closed operator on the space of all continuous functions. And also, we can see that when a function is in the domain of this closed operator, so the answer is if and only if this limit exists. And also, yeah, it's compatible. This delta bar and the partial bar, they are compatible under the continuous functional calculus. Okay, so far these are some technical results. And we proceed to solve this exponential equation, partial bar g equals to g partial bar f. And now this becomes delta bar g equals to g delta bar f. So this relation, just use the definition of delta bar. We can just have this explicit form is gx minus gq square x divided by x minus q square x equal to gx fx minus q square x divided by x minus q square x. Okay, so just by the cancellation, and we can find a recursive formula for g. Gq to the 2n equals to g to the 2n minus 2 times 1 minus f q to the 2n minus 2 plus f q to the 2n. So we can have a just product formula for gq to the 2n's. Just if we know g1, the initial one, then we can use f to get the value explicitly for all gq to the 2n's as a function on the spectrum of B0. Okay, yeah, so this is a good formula. And it's easy to show that if f is in the domain of delta bar, then g is also in the domain of delta bar. And g is invertible. That's not guaranteed. And we see that g is a product of this thing. So of course, g is invertible if and only if all of these factors are non-zero. If one of these factors is 0, then g is no longer invertible. Yeah, so that's an important observation. So by the way, if g is invertible, then in this case, g inverse is also in the domain of delta bar. That's obvious because we have explicit computation formulas for g inverse and the domain of delta bar. Okay, so inspired by this, we have a definition. We say that f has a defective spot if this fq to the 2n minus 2 minus fq to the 2n equal to 0 for some n. Okay, and we denote it by sf. So the first theorem we get is, yeah, if f is in the C-star algebra of 1B0, then this anti-holomorphic connection lambda bar partial bar f is gauge equivalent to the standard one if and only if we don't have defective spots. Yeah, so which means that if we have a defective spot, then it will appear in the product. So the g is not invertible. Then we have a non-invertible non-zero solution to this equation partial bar g, g partial bar f. Then it cannot have an invertible solution. Okay, so that is the first main theorem. The non-standard anti-holomorphic structure does exist. Okay, more explicitly, the formula, the element B0 divided by 1 minus q squared. So it's easy to see that it has a defective spot at 1. Yeah, because we have this coefficient, then yeah, the difference between the value at 1 and q squared, the difference is exactly 1 if we have this B0 minus q squared. So in general, this, if we multiply the q to the 2n minus 2, then it has defective spot at n. Then in particular, we have this B0 to the infinity. This element, it exists in the C-star algebra and is in the domain of partial bar, and it satisfies partial bar B0 to the infinity equals to B0 to infinity times partial bar B0 minus 1 minus divided by 1 minus q squared. And so this B0 to the infinity, so just B0 is a diagonal function. And if we raise its power to the infinity, then the value is 1 when at 1, and the value is 0 for any x smaller than 1. Yeah, so this is a continued function on the spectrum of B0 because the B0, the spectrum is discrete except at 0. So this B0 to infinity is a non-invertible element, and it satisfies this equation. So this means that we cannot have an invertible solution to this equation at all. Okay, so the explicit example is lambda bar partial bar B0 1 minus Q squared is not gauge equivalent to the standard anti-holomorphic connection. Okay. Yeah. So one thing is, let's go back to our first attempt. We say that, yeah, the radius of convergence is 1 over 1 minus Q squared. So yeah, so this example, it's compatible with this attempt that is 1 over 1 minus Q squared is the cutoff point. So smaller than that is all good. And now we found that equal or bigger than that is indeed bad. So at least in some cases, yeah. So by the way, Polish check found similar results, the non-existence of this solution to the exponential equation, so the existence of non-standard holomorphic structure for non-commutative two tori a long time ago. I think it's in 2006, and now we found it for quantum CP1. Okay, so this is the first main result, and the second thing, the next thing is now we have non-standard anti-holomorphic connections. So when are they gauge equivalent to each other? That's a question. So the first result is using similar method. We can show that if two functions, they are both in C-star algebra of 1B0, and if they have the same defective spots, then they are gauge equivalent. And we don't have the inverse result by the technical difficulty before. So we don't know whether this, if we have a non-zero, non-invertible solution to the partial bar G equal to G partial bar F minus partial bar F2G, partial bar F1 and F2G. If we have a non-zero, non-invertible solution to this one, then whether or not we have a invertible solution to this one. So we cannot use the same method to find the gauge equivalent problem for non-standard holomorphic connections. However, we found another way to solve this problem. So first, we focus on L0, and second thing is no matter whether the anti-holomorphic connection is standard or not, we can use just general results to show that the kernel of the connection is finite dimensional, by some spectral triples argument. Yeah, so it definitely has finite dimensional kernel. Of course, in the standard case, the kernel is just one dimensional. It's just holomorphic functions. And in the non-standard case, no matter how non-standard it is, it's finite dimensional. That's some general result. And of course, the dimension of the kernel is an invariant and the gauge equivalence. Okay, so now we will give a lower bound of the dimension of the kernel in some cases. So we will find that in some non-standard anti-holomorphic connections, the kernel has dimension maybe 2 or 3 or 4, or at least 2 or 3 or 4, or so on. Okay, the way is we go a little bit out of the C-star algebra generated by 1 and B0. We go to the C-star algebra generated by is of the form f b minus to the nth power, and where f is in the C-star algebra generated by 1 and B0. Okay, so by some calculation, we can see that if theta equals to partial bar of h, then the lambda bar theta on f times b minus to the nth using the explicit partial bar operator defined on B0 and B minus, we can see that it satisfies this complicated relation. And so when it belongs to the kernel, so of course it's just the parenthesis is 0. So this means that the h is given, so we want to find f such that it is 0, then f needs to satisfy this product relation in this way. Okay. So now another question, important question is, when does this product converge? Observation is it almost never converge because we said q is smaller than 1. So the denominator is strictly smaller than 1. And the numerator, we see that h is a continued function. So the 2h, hq to the 2n plus 2k and hq to the 2n plus 2k plus 2, they must converge to the same number. So the difference must go to 0. So the numerator, we have limit 1, and the denominator is strictly smaller than 1. So the product seems that it's definitely diverge. But of course, there's one exception, that if for one term the numerator is 0, then it will remain 0 all after that. So no matter how big the other factor is, the product is still 0. Yeah. So when it is 0, yeah, so there is a possibility that the numerator is 0 for some k. So although the ultimate limit will be 1 for the numerator, but it may be 0 at some place. And the answer is when it's 0. Yeah. So that is if sometimes the numerator has a defective spot. So, and a careful look at it, we can see that if n is smaller than the maximal size of the defective spots of h, then we can find a continuous a solution to the above equation such that the f b0 to the nth is indeed in the kernel. Okay, and moreover, using the faithful representation of the C-star algebra b0, b minus, b plus we mentioned before, we can show that, yeah, for different n's, this f b0 to the nth, they must be linearly independent. Okay, so the consequence is for any h, the dimension of the kernel of lambda bar partial bar h is greater or equals than the maximal of the defective spots of the defective spots of SH. And in particular, if we take h to be b0 divided by q to the 2n minus 2 times 1 minus q squared, then we said that we can directly check that the defective spot is n. Then the dimension of the kernel of this is at least n. So it could be bigger, but we don't know whether it's bigger or not, but actually it's n. It's at least n. Okay, and this result, this fact, together with the finiteness of the kernel, of the dimension of the kernel for any connection, anti-holomorphic connection, it's produced the following theorem. That is, we have at least countably many different gauge equivalent classes of anti-holomorphic connections on L0, hence on Ln. Yeah, the reason is if we have only finitely many, then their dimension, each of them has finite dimension kernel, then the dimension must have an upper bound. But we don't have upper bound because, yeah, the dimension can be as large as possible. Yeah, so this is another main result of of our work. So by the way, in last summer, we tried to find some other solutions in the kernel using the formula of, oh, sorry, I have a typo here. It's not b0 to the nth, it's b minus to the nth. Yeah, sorry, so b0 to the nth is still in the same theta algebra. So I need to correct this. So so it's b minus to the nth. So, I want to, yeah, here is right, b minus to the nth. Yeah, b minus to the n, f times b minus to the n, that is good. So what I would like to mention is we want to find, in the same way to find solutions in the kernel of lambda bar theta in f times b plus to the nth. And it seems that we found a lot of solutions, but actually they turned out to be all zero. Yeah, so that is a phenomenon here in the CP1Q. So formally, we have a lot of solutions, but actually after careful look, they all cancel. They are not linearly independent, and actually they are all zero, so they don't count. However, for B minus to the nth times F, yeah, they are genuine solutions and they are linearly independent. Yeah, so actually we even find some non-trivial holomorphic functions in that way, which doesn't make sense. And later we found that they are all zero. So yeah, they look like a big expression, but they are zero. Okay, so yeah. Anyway, so I need to correct this typo. It's FB minus to the nth in both cases. Okay, we have at least countably many gauge equivalent classes of anti-holomorphic connections on L0. Hence, using tensor product, the same holds for Ln. Okay, so let me briefly mention that some further work in our mind. The first thing is we want to have a complete classification and parameterization of gauge equivalent classes of anti-holomorphic connections on Ln. So as you can see, our method is not very direct.
Yeah.
We just use some indirect method to show that there are many non-standard anti-holomorphic connections. But of course, it's good to have a direct classification of everything. I think Dr. Green, they did some work along this line. And another thing is we observe that our non-standard anti-holomorphic connection is on the line bundle. The complex calculus, the differential calculus on the base manifold CP1Q is just the standard one. We just change the holomorphic structures on the line bundle. Yeah, it will be interesting to see if we also have non-standard complex structures on the base manifold CP1Q. Yeah, so in the classical case, there's no. So CP1Q, there's only one CP1Q. I think Riemann already knows this. Yeah, and in the quantum case, I'm not sure we can have a similar non-standard holomorphic structures on quantum CP1Q. So, and of course, another problem is can we generalize everything to CPNQ and more general quantum Grassmannians or quantum flag varieties? Yeah, so this will be interesting. Okay, I think that's all I want to talk about today. Thank you very much.
Thank you.
Thank you for a nice talk. Thanks.
Yeah, thank you.
Great. Now it's time for questions. So do we have some questions?
Yeah, maybe at least.
Masood, do you have some questions?
Yeah. So yeah, okay. So it's okay. So well, thank you, Zhaoting, for the nice talk. Can we go to page 21?
21. Yeah.
You find this Q differentials?
Yeah. Is this page? Yeah, you're talking about?
Is it 21? Page 21?
Yeah, this is 21. So now you're making.
Oh, okay. Yeah. So right. So what I'm wondering is, did you define this? Yeah. For example, let's look at top of the line, delta bar of F. This Q del bar operator, right?
Yeah.
This Q del bar, you define it like that. I mean, so where is this F?
F is a function. Yeah. Yeah, it's we can just define the first F could be monomials. Then it's just this way. And then we can extend it to polynomials by linearity. And we can, yeah, it's not easy to prove, but we can prove that the delta bar is a closed operator on continuous functions. It's a closable operator. Yeah, so this F could be some functions. And
can we turn this off? Yeah, some of this. Okay, okay.
Okay, do we have some further questions?
So by
Yeah,
the way,
but
I would like to comment a little bit more that this B0 to the infinity is in the domain of F. So this is not a polynomial, but it's in the domain of F. So that's, yeah. Sorry, it's in the domain of the delta bar. So that's, yeah. Other
Right.
question?
So it seems that you have a question, right?
yeah, I'm just trying to see which one. Yes, so I mean, the natural thing you'd think would be that you'd weaken the notion of gauge equivalence. But then, I mean, have I understood correctly that for the different non-standard structures, then you had a kernel which had a different dimension. So, I mean, having some generalized notion of equivalence where the dimension of the holomorphic sections was different would be a bad idea. So yeah, it's very mysterious.
Yeah.
Maybe another comment rather than a question is that, yeah, if you're trying to extend it up, this argument from CP1 to CPN, one thing that you have, so this element B0, B sub 0, the analog of that exists for CPN, and the C-star algebra generated by it behaves just as nicely. So this is already there for you. This has already been used in the paper of Jens Kade and his PhD student, whose name I don't remember, where they did the compact quantum metrics based stuff for CPN, extending what they did for CP1. They used the C-star algebra generated by B sub 0 and its higher analog
Okay.
very much.
Yeah.
So that's already there.
Mhm.
That's a good start to extend.
Yeah.
The bad news is that if you try to do this, then for the Grassmannians, the subalgebra, the natural subalgebra that you're looking at becomes far more complicated. But for CPN, it should be okay.
Yeah. Yeah.
Can I go back to my question because I couldn't ask it.
Yeah.
But that was exactly this formula. Yeah, you're right. So this can be defined for polynomials like that. But I think the problem is these smooth functions on this quantum sphere. I mean, there is no easy description. You see, that's different compared to the work of Polishchuk, where you have very nice description of the smooth functions in terms of Schwartz polynomials and all that.
Yeah.
So I would like to know how to extend this del bar to class larger than polynomial functions on the quantum sphere. I mean,
yeah.
so
So
you say there is an extension, yeah.
Yeah. The point
Yeah,
is
but
the delta bar. So we just extend it on this C-star algebra, generated by B0. Then, it's a closed operator, and so a function is continuous and is in the domain of delta bar if and only if this limit exists. So this is what we can prove. And in particular, we have a concrete example, this B0 to the infinity. So B0 to the nth is a polynomial, but B0 to the infinity is not a polynomial.
no,
Yeah,
it's not
it's just it's like a step function, but it's fine in our spectrum because we don't care the break between at one. So this is in the domain of delta bar. So yeah, this I think this one example is already enough to say that okay, non-standard anti-holomorphic connection exists. Yeah, so this B0 to the infinity is a classic.
I see. Yeah. So Polishchuk result was that exponential is defined only some small neighborhood of 1 or 0.
Yeah, I think so. I don't. Yeah, I should say that. Yeah, I don't. I'm not so familiar with his result, but at least he found that only in some subsets, this exponential equation has solution, and in some subset it has no solution. So yeah.
Yeah. Okay. Very good. Yeah.
Thank you.
Do we have more comments or questions? Maybe from the
have one
Prague
question.
audience
Quick
or
question.
Freddie?
Yeah, thank you. I have a quick question. So you have this delta operator. So what do you mean by closed operator? This is defined in the sister algebra.
Yeah. Yeah. So by closed operator, we just consider that sister algebra as a Banach space, and closed means it's a closed operator in the in the sense of functional analysis. That means more explicitly, that is, if we have a sequence approach to an element, and also the delta bar of that sequence also has a limit, then this limit is well defined. So we cannot have two different limits. Yeah, so this is
Okay.
the Mhm.
So so the domain is not in a Hilbert space. It is in a Banach space.
Yeah, it's in a Banach space. Yeah,
Okay, thank you.
yeah, sure.
Last chance for comments or questions. Okay, seems there are no further questions. Then let's thank Zhaoting for a great talk and for both speakers. Thank you.
Thank you. Yeah.
And yeah, very good. I think this was the last talk of the Prague seminars, or are there more coming? Otherwise, I can announce the
This-
next one. Maybe you can remind me.
I think this is it until October.
That's it. So summer break,
Yeah.
very well. So
Yeah.
great time, and yeah, see
There might
you.
be one more seminar, depending
Oh.
on if we can secure the speaker around end of June, early July, potentially. But that is not secure yet, so TBD.
Confirmed. I see.
Yes.
Okay, very well. Okay, thank you for joining. See you next time. Bye bye.
Bye bye.